All right. Flat here. So what we're going to do today is basically go over some retrosynthetic analysis, and it was E.J. Corey who's basically been credited with developing the strategy, and we would have sort of talked about this a bit in Organic 2 when we did that. Basically, the way that this works is that the key point is that you work backwards from your target molecule, and in doing so you generate a series of intermediates that can be formed from either other intermediates or simple starting materials. And the way that, readily available starting materials is pretty key here. You don't want to break the bank when you're designing a synthesis by having something which is either very hard to make itself or extremely expensive. So something which is commercially available is the best way to go. So there's a special arrow that's used in retrosynthesis. Let me go up a bit, sorry. That being this arrow that is sort of open-ended on one side and it's got a point. And so the open-ended side is the product and the pointy side is your starting materials. So your target molecule will be made from A and B. B will be made from E and F. E will be made from G and H. A would be made from C and D, that type of stuff. So the way that I've drawn this synthesis here, this little retrosynthetic synthesis here, what classification of synthesis would this be if it was built like this? Do we remember?
Convergent.
So if you had your starting material and you did one step to make A, another step to make B, another step to make C, another step to make D, another step to make your final product. This type of synthesis had a specific name. And if you had, say, starting material number 1, which made A, starting material number 2, which made, say, B, B made C, A made D, both of these come together to make E, or that sort of synthesis had a other type of name. Right, the first one's linear. Yep. And this one here, which would be very similar to what I've drawn here because of, G and H would make E, F plus that would make B. This whole mess would be very similar to this one here. And it starts with C.
Convergent.
This would be a convergent synthesis. So this retrosynthesis here is very reminiscent of a convergent synthesis. So you've got various sort of places. You're starting from two different areas and you're bringing them together to make a larger molecule. No, I can't. Wait a second. Okay, someone say something.
Hello.
Okay, so were people just talking and I didn't hear anything?
Yeah, Joel kept saying the answers.
Okay. Sorry about that. I had my speaker off because I was in a Zoom meeting yesterday and we were getting lots of feedback. So I turned off my speaker and I didn't turn. So actually I went through a whole class this morning without my speaker on and I didn't even realize it. Oh boy. Okay, anyway. All right, well, I'm glad that, Joel, you were saying the answers there. Okay, excellent. Okay, okay, good. Now, where was I going here? Oh, the joys of online, Okay, so these simple starting materials, depending upon who's writing the textbook, you would either call those syntones or retrons. I think the syntones is the more modern version of this. So that's just a little classification. Now, when we're doing this, if you're designing a synthesis of a large complex molecule, you should build into it a couple of key important things. And sometimes it's not always possible, but the successful ones often do include these. Okay, so it's good to have a flexible synthesis so that there's a number of different potential approaches that you could make. So if you are, like in the previous example here, so if this target molecule has got, the final step is basically having molecule A coupling with molecule B, you would have a number of different approaches to say both A and B to make it flexible. So here it says, well, we can make it from C and D, but if C and D doesn't work, you would certainly hope that there was another version where you could make this from F and G. And this step, when you're putting A and B together, because you've made two like relatively complex intermediates from that, you'd want to make sure that that last step is reliable. So that's probably the very next thing you'd want to do. So generate simpler, less complex intermediates from cheap, readily available starting materials. So again, you don't want to, this is sort of what we said at the start. So start with readily available materials, make sure your synthesis is flexible. And probably the third point, which is the hardest one to keep in mind, is that make sure that all steps are subject to reevaluation. And this, sometimes you have a designer reaction that you want to use in the synthesis, and the whole point of choosing the synthesis was because you wanted to do your designer step. And so it's not uncommon to see a lot of sort of wasted effort to set up that actual step. And if it works in the end, great, super. So there's a little bit of, it all depends if you've got that secret reaction in your back pocket that you want to use. If you can do a reaction where A goes to B, B goes to C, and then your super reaction, your designer, I guess I'll call it designer reaction, goes to D. It's, if you have to go like A, B, C, D, E, F, and then to this one to do this designer reaction, and you're wasting all these steps just to set that up. That's probably not the most efficient synthesis in the world. It works, so, but anyway, that's a commentary of, it's just a little color commentary there. So, but so if you allow for all steps to be subject to reevaluation, then this is ultimately going to make a better synthesis. It's like not having a favorite child, I suppose. Not having a favorite reaction. So anyway, so here's a relatively simple example. We've got, let's see, there are 1, 2, 3 broad functional groups in this molecule, and the way that if you're using, instead of A, B's, and C's, say we've got our molecule here, the way that these things are done is a little squiggly line is basically drawn through the bond that you want to break. And this will be what we call the disconnection. So we are going to disconnect between the nitrogen and the carbonyl of the amide. And so this is going to generate 2 syntones from this. And we've drawn, so these are basically idealized reagents, down here. It's not the thing that we would use in our, you wouldn't get that out of the bottle. So if you're unless you're doing radical chemistry, when you're breaking this bond, one side is going to have the positive and one side is going to have the negative. One side's effectively the electrophile, one side will be the nucleophile, so to speak. So when we're breaking this bond, basically imagine what each one of these things would come like. So the easiest way to do this at the start is to use these things with positives and negatives, and then later on we're going to see what this nitrogen with a negative would look like, or what this carbonyl with a plus, what the actual reagent would be. The other 2 functional groups in this molecule are what? We've got an aromatic, we've got 2 aromatic rings, and the last one is
nitro group.
Yeah, the nitro group. Okay, so we've got our 2 components, our 2 idealized reagents. And the electrophile, the carbonyl with the positive charge, the most common sort of equivalent for this is the acid chloride. And the nitrogen with the minus, well, the simplest one is just basically an amine. So in the next couple of slides, it's going to have a whole list of like acceptors, positive charge, I guess we would call this an acceptor. Negative charge, we would call this a donor. Nucleophile, electrophile, so to speak. Now, what we didn't do is we didn't break this down with like the negative charge on the carbonyl and the nitrogen with the positive charge. Why didn't we do that? And this would go back to sort of some of the stuff we talked about at the start of Organic 1.
Would it just be they'd be reactive, like by themselves? And wouldn't necessarily do what we wanted.
Okay, maybe I'm asking the question wrong. So like if we were, why didn't I make the nitrogen with the plus the acceptor? Why would that be challenging and this being the donor?
That would mean you're making your nitrogen like more positive than it already is. Right. It's only a 5 octet.
Right. So nitrogen, if you think of nitrogen and carbon, so carbon, if you you bond it to a nitrogen's got lone pairs. Nitrogen is a Lewis base. So it's got the nucleophilicity sort of built into it already, right? Carbon, to make it an electrophile, all we need to do is basically attach a electronegative atom of some type to it, right? To make carbon into a negative takes a bit more work. And certainly to make nitrogen into a positive takes a bit more work. So we're going with the what they do best. Now, it turns out you can make a carbonyl with a negative charge. It's not drawn in such a fashion. We might get into that a bit later on, but
do carbonyls deal with having like a positive charge on them better too, don't they?
Well, like a carbonyl just by itself is already innately got that delta plus there, right? So it's already an electrophile. And so if you do what we did up here, when you attach a chlorine, now it's electrophilic plus the chlorine is basically a leaving group. So it's easy to make that into a really good acceptor fragment, so to speak. So now the key point here is, which is we're going to see, is where to make these. The hardest part to any sort of designing a synthesis is figuring out where to break those bonds. The more reactions that you have knowledge of, the easier it is to do. So at the start, there's a certain number of tools in the toolbox, and as you add more tools to it, then these disconnections become easier to sort of visualize later on. Okay, so basically now, the next step is that, so we figured out that we needed, this is our acceptor fragment. But you can't buy this through the chemical companies, or if you can, it's super expensive. So what chemists have done is they put this little, okay, well, we can make this acid chloride from this. So this is basically this disubstitute aromatic. This acid chloride can be made from this benzylic carbon. And we can do that through what we would call a functional group interconversion. So we can't buy this in the store, but we can start with this readily available thing, and we can do some functional group interconversions to make that acid chloride. So they would just call this FGI, and then boom, this is where we would start from. And this would be commercially available. So it's a para-substituted methyl on one side, nitro group on the other. Now, the functional group interconversion that they would probably do, based upon what we did in Organic 2, would be that the benzylic position itself is susceptible to oxidation. So what they would probably do is oxidize this to the carboxylic acid, and then convert this to the acid chloride using thionyl chloride. That's a typical reagent. This guy. And the reason why this acid chloride over here is probably super expensive if you were to buy it by itself is the fact that this nitrogen is a really strong electron withdrawing group, and this carbon already has a really big delta plus because it's an acid chloride, and they always do. But with that electron drawing group, like water should be attacking this like crazy. So what you'd want to do is make this and react it, like not ship it across the country or whatever. So that's basically how this would work. So they would start with this, and then they would do an oxidation and converting the carboxylic acid to the thionyl chloride. So yeah, so if this isn't available, functional group interconversion to something that is simpler. So, and there's lots of functional group interconversions that we can do. Yeah, and here's the next part. The most difficult task is in designing is to where to make the disconnection. So there are some simple rules for making disconnections that we'll go through. But before we get to that, any questions so far? Okay, well then, here are a list of some of the acceptor syntones. So our plus basically just attach a leaving group to it. Chlorine, bromine, iodine, tosylate. We didn't really see this much, the phenyl group with a positive charge. It's probably going to spell this wrong. Diazonium salts are an equivalent of phenyl with a plus. This nitrogen is a super leaving group, and of course it makes nitrogen gas. And so they're quite explosive. So they can be tricky to deal with. All of the various carbonyls with positive charges, you can basically usually just add either a chlorine or conceivably an amide or an ester. So those can be the leaving groups necessary depending upon the type of reaction. If you need to make a carboxylic acid, you can start with dry ice. And then if you need to attach groups on the beta carbon to a ketone or the beta carbon of a nitrile, you can use double bonds. So both of these are what we would call Michael addition or 1,4 addition. We'll see that in a little while. Oops. A simple primary alcohol, we could use formaldehyde. And if you would need a secondary alcohol, you could use aldehydes or ketones in the case of a tertiary. And what we'll see a bit later on is that if you have a hydroxyl group on the carbon, you've got a carbon right next door to where you want to make the bond, you can use just a straight up epoxide. So whatever nucleophile you have can attack there and you'll open it up. And the fun thing about carbonyls is that if you have a leaving group on the alpha carbon, then you can use this as the acceptor and just use that like a bromo ketone, alpha bromo ketone or something like that. So those are some of the common acceptors that we'll see. And when it comes to negative charges, donors, so carbon with a minus, well, we have our friend the Grignard reagent here, alkyl lithiums, organocuprates. These are good for 1,4 addition. We used to talk about these a lot in organic too, but as time's gone on, I've gotten slower at getting through stuff. So that usually gets left out. Nitriles, you just deprotonate it. Triple bonds, so you would just start with like the original one are why is my pen not working anymore? Terminal, triple bond, and just deprotonate it with an alkyl lithium or a Grignard reagent. Now, what everyone who's taken organic 3 has seen, negative charge on the carbon beside a carbonyl. These are what we call enolates. And this is a super important reaction. We saw this before, the Wittig reagent. And a negative charge beside a nitro group. This is basically the nitro equivalent of an enolate. So this is, you just deprotonate one of these protons here. And so here, I guess I should draw it a bit better. If you've got a ketone, you just remove one of these protons here to make that. Right, okay. Now, this is I don't know why I put this here. It's a bad place for it, but anyway. This is Robinson's synthesis of tropinone. We will come back to this in a little while, but it's a rather unique and elegant, I would say, synthesis of a like it's a small molecule, but it's got some symmetry associated with it, and you can basically break this apart if you do a hydrolysis reaction, so that you're breaking both of these bonds in addition to these bonds. And so if we put a little star on acetone, that would be these 2 carbons here, and a circle around the 2 aldehydes, that would be these 2 carbons here. And all of these things can be mixed together and theoretically, and you would end up with this. And so the way that they did that was with this synthesis. And once we understand some of the chemistry we're going to do in a second, we'll come back to this and see how this works. So these carbons here need to be nucleophilic. These carbons here need to be electrophilic. And you've got this guy in here doing who knows what. So we'll get to this in a little while, and then make that. And you've got also have to lose these, which is interesting. So we'll talk about that a bit later on. Yeah, I must have. This is all of these notes were made a long time ago, I think with overheads, and so this overhead must have got stuck in the wrong place. So, but anyway. So some of the guidelines, this is where I wanted to go. Okay, so you want your disconnections to correspond to known, reliable, hopefully simple reactions. And that is, unless of course you want to do some research to invent a reaction. So this would be developing a methodology. Wouldn't it be nice to be able to do a transformation like this? It doesn't really exist in the literature. Let's develop it so we can use it in situation X, Y, and Z, right? So this is a whole different, one of the other classifications of organic synthesis. So what we would be doing before that, like now you'd want to use known reliable reactions. So this molecule here is 2,4-D, which would be a pesticide. And based upon what we had before, like some of the acceptors and donors, we should be able to, in a little while, figure out where the best disconnection would be to make this molecule. I don't expect anyone to answer that quite yet, but we will see how, keep this molecule in mind for a minute or two, like going forward. Because the second guideline is going to help us. So for compounds consisting of two fragments joined by a heteroatom, so heteroatoms are things like oxygen, sulfur, nitrogen. The best disconnection is often next to the heteroatom. And these two examples here, there is a specific side of the heteroatom which is important. So I'm going to draw basically two little lines here, A and B. Heteroatom nitrogen here, C, D. So for each one of these, one of the disconnections is far better than the other. So for the molecule on the left, this one here, would it be A which is better or B which is better? So remember, you want an acceptor and a donor. And the interesting thing about, for compounds consisting of two fragments joined by a heteroatom, oxygen, sulfur, and nitrogen, all of these, all of these things, what they have in common is they have lone pairs, right? So if they have lone pairs, the side with the oxygen, the sulfur, or the nitrogen, that's going to be the donor. So the other side's going to be the acceptor. So we're going to have O minus, S minus, or N minus is our theoretical, or is our idealized reagent. So do we want, so said another way, do we want it to be we want it to be, this would be, this would be the B version, and this would be the A version. Any idea?
Would B be better because it's easier to make that carbon positive than a carbon on an aromatic?
That would be my thinking, yes. Okay, so this, okay, good. So if we wanted to use this one as our acceptor, we're going to need to use that diazonium salt, which is explosive. And it might be a known reaction, but if I can avoid something which might blow up in my face, yeah, I'm gonna do that. So like a positive charge on the carbon which is attached to an aromatic, the benzylic position here is quite reactive. So you could just use a benzyl bromide or a benzyl chloride, and this could be your reagent, or this could be your actual commercially available compound here. Whereas if you needed to make the diazonium salt, that would be far harder. And then your other component, well, this is just the sulfur, if we just had like the thiol, it's going to be stinky, but could probably get away with using this as our other component. So these two components are going to be a nice thing if we're disconnecting B. So something similar would be something similar for the same molecule over here. I'll erase over here. Oops. The D disconnection would be better because you could have nitrogen with a negative charge, which is what you want, and then the R carbon. If you just had like a Br here, this could be, you could do potentially a SN2 reaction. There is actually a better one to do if we had, we'll see a bit later on when it comes to synthesizing amines. There's another way of making amines that's slightly more reliable. SN2 reactions or SN1 reactions can be slightly problematic. So there's what we would call a reductive amination, which in this case, instead of being a bromide, you could have an aldehyde. And we'll see how those work. So an amine plus an aldehyde can actually make a carbon-nitrogen bond. But we'll get to that in a second. So the first, like if you've got a heteroatom in your molecule, disconnecting beside those atoms is the best bet for absolute for sure. Okay, I gotta erase this little thing here. The third point is that you want to avoid what we would call chemoselectivity problems. And so what this means is that you want to disconnect at the start the most reactive groups. So you want to add reactive components at the end. Because if they're present in your molecule, you always have to worry about side reactions. So this is a natural product. I can't remember exactly where you find it from, but there are a number of different functional groups in here. Any idea as to which ones would be reactive? So what are the different functional groups in this molecule?
Some alcohol.
Okay, we got alcohol. Alcohol. So the alcohol, it's got an acidic proton. Okay, what's another one?
Ester?
An ester. Okay. So we actually have two esters here, right? We've got this one, and we've got this one. Okay, now, are those two esters equivalent by any chance? So it's a cyclic ester. So these are both cyclic. And so there's a special name for a cyclic ester called a lactone. So I'll erase these cyclic esters here. It's conceivable that the 5-membered ring ester might be slightly more reactive than the 6-membered ring one, but that's probably a stretch. So we've got an ester. How are esters reactive? So we have to worry about strong nucleophiles. All right. What other functional groups do we have? So we've got double bond, double bond, double bond. We have got an isolated alkene. And alkenes, they tend to react with electrophiles. And we've got an alkene which is beside this, which is conjugated to the ester. So both of these are conjugated to the ester. So if it was conjugated to a ketone, we would call this basically an enone. So alkenes are basically reactive with electrophiles, and enones, they can react with, they can do 1,4 addition with most nucleophiles. So these are quite electrophilic. So which group is the most, which one would you want to probably install last? Well, the acidic proton alcohols, these can be protected with protecting groups. So we don't have to really worry about that too much. If you're not using a strong nucleophile, then your ester should be fine. And if you're not using a really good electrophile, the isolated alkene should be fine. It's these enones which are the most reactive, because like water can react with these, or nitrogen, or any sulfur containing compound. So you'd probably want to make those last. And I believe that during the synthesis, those were both made at the same time in the final step. And we'll get to that in a little while. So you want to if you have a reactive functional group, you want to disconnect this last. And this will be the next question. So this intermediate, some pharmaceutical company was using this to make an anti-obesity drug. So we've got 2 oxygens in here, and we've got a nitrogen in here. And if we follow our rule about disconnecting next to a heteroatom, there's 4 basic places where we could disconnect: here, 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 or here. When it comes to, if we want to avoid chemoselectivity issues, the most reactive group in this, we've got nitrogen, so this would be an amine. We've got oxygens, and they currently are in the form of ethers. So the most reactive group, and we got aromatic ring, which we wouldn't want to disconnect around anyway. So the most reactive group here is the amine. So we would want to make that disconnection the last disconnection. So in other words, we want to install that nitrogen at the very end of the synthesis. So if this was your synthesis, you would want to either break number 3 or number 4. That would be your last step. It turns out one of these 2 is slightly better than the other one. And I think on my next slide, I actually say what it is. So I'll, yeah, this breaking 3 is the best, because what we would end up with is, so nitrogen's the donor, and we need an acceptor over here, oxygen X. We could call that a bromine or something like this. Remember, pH equals just an aromatic ring phenyl group. So we could do a simple sort of SN2 reaction here, and we would end up making our final product. So yeah, you want to add the nitrogen last. And this is better than if you had plus the rest of the molecule. Mainly because the now you've got a reactive group in the rest of your molecule. So is this undergoing, like, how do you make this? Are we putting this on next? Like, having this group, this is going to be the most reactive part. So I don't know how you attach to make the rest of the molecule with that present in it. So it's always good to do the last, attach the last thing first. So if 3 is the best disconnection, then we are left with doing a retrosynthesis of this component. And if we follow our same rule about disconnecting beside a heteroatom, we could disconnect here or we could disconnect here. And which one is better? So if we disconnect 1, we would have this 1,2-dibromide and this phenol. And if we disconnect 2, we would have this phenol and this benzyl bromide. But one of these 2 disconnections is better than the other one. Any idea which one? Okay, so let's do the analysis this way. If you look at, I'll label all of these different letters. Okay, so A, B, C, and D. Electrophile, nucleophile. So is molecule A an electrophile, a nucleophile, or both?
Electrophile.
Right, so delta plus, delta plus. So fragment A is purely an electrophile. Good. Okay, if we look at fragment B, is it an electrophile or a nucleophile? So we've got this oxygen's got some lone pairs, so we can attack. There isn't really a place on this which is a particularly great electrophilic site. So molecule B is a pure nucleophile. So if these 2 are going together, nucleophile, electrophile would work great. Molecule C, is this a nucleophile or an electrophile?
It's an electrophile again.
Yes, delta plus, delta minus, leaving group. So this is an electrophile. Okay, and in the phenol number D, is this a nucleophile or an electrophile?
Both.
Right. We've got one end which is nucleophilic and one end which is electrophilic. This would be basically a nightmare to deal with, because this is both. So if you want to make this molecule D attack C, and you say deprotonate this, what's to stop it from reacting with another molecule of starting material of itself? There's nothing to stop it from reacting with itself. So here we would run into some problems where once you deprotonate here, if there's another molecule of this in the reaction flask, when it could react with itself. So you could get some coupling with, so disconnecting one would be the far better connection between the two. And so it's, yeah, so that's basically where I was going with that. And the fun thing is this reaction, to make this compound here, you could start with the diphenol and react it with one equivalent of your, so nice, I'm sure that's how they did it when they were doing the whole, it's very nice symmetrical sort of synthesis there. Okay. What time is it? 12:30. Okay, so why don't we take a short break, and then we'll talk about amines and that sort of stuff, because there are some questions that I'll pose. Well, it's not quite as, if you've got a leaving group here or a leaving group here.
I was just saying that there'd be so much like steric interference that like it's so less likely to happen there.
Yeah, that's why using a ketone and doing a reductive amination would probably be a better, more reliable sort of reaction. But we just learned this one, so it's kind of, it's sort of, I just wanted to reinforce that that's why we would try to do that. So this is, yeah, so this would be the first one to make the amide and your secondary amine. And then if you break this and use the ketone plus your amine, or the orthomethoxy aniline, then this would be probably the best way to do this. I'm gonna go back to sharing the other screen. I sort of recorded, I sort of screwed up and didn't record everything from the start. So I'm just basically scanning this. So if you need to look at it again, you can. Anyway, let's go to where we were. Now, with regard to, if you would need to make a primary amine, like this is interesting here. If you need to make a primary amine, like this guy, and it's got, like, it's attached to a carbon with multiple different substituents, you can do a very similar sort of reductive amination, either using the oxime, which is this functional group, or just using NH2, making an amine, and then reducing it. These guys are quite unstable. Sorry, the amines, unsubstituted amines, are quite unstable. So this is why sometimes oximes are used instead. But the overall effect is very similar. You generate a carbon-nitrogen double bond and then reduce it. In this case, you're also reducing off the hydroxyl group. If you need to make a primary amine and at the same time insert a carbon, then the best way to do this is an SN2 reaction of some sort of alkyl halide, you make your nitrile, and then the nitrile gets reduced using lithium aluminum hydride. The second step, of course, would be acid, and you would get your primary amine. Yep. So for primary amines, yeah, you can use cyanide, or you can use via oximes or unsubstituted amines. I have a little thing right down here at the, oops. Think about this before next class, how you'd make this using all of the various functional groups that we've come across. There's actually a couple ways how you can make this little guy here. Don't worry about putting on the CF3 here, because this will be part of the starting material, but just give this some thought before next class. There's a couple of things I need to do. Sometime before the end of the day, I'm going to send you the experimental protocol for the first lab. So next week it'll be Kirsten, Christian, Brock, and Josh. So we'll do the lab this coming week. You guys all did Organic 3 last term, so you will have seen all of these things before. So it'll be it won't be as much of a, you would have seen all of these techniques before, so it'll be probably relatively straightforward. But for everyone else, you'll get I'll send out the protocol. I'll include some diagrams as to what we're going to be doing in it. So I'll just do that before the end of the day today, or first thing in the morning. But what we'll do is on Tuesday we'll proceed from this point on using NH2- reagents that are equivalent to this, because this is a very basic type of reagent. Because I think class is just about ready to end. Were there any questions on anything we did so far today?
I just have a question about like our upcoming stuff. Like, I'm just asking, how are we presenting like our reactions? Like the first one's reduction or something. I can't quite remember.
Yeah, it's a reduction.
But we're essentially doing it the same type of way, how you kind of gave us your example.
Yeah.
Okay.
So far only one person has said, oh, I've got a good reducing agent I want to do. So let me know which one you're doing, because we don't want to overlap stuff. So, and if you are having trouble finding a good one, let me know, and I can surely say, well, how about this, or how about that? And I can't remember what, because I did the Birch reduction, and I can't remember when I suggested everyone evaluate it for me. When was that?
I want to say the 21st.
Okay.
I could be wrong.
That sounds probably right.
I think it's I have it written down as 20th, but 21st makes more sense because it's a Thursday.
Yeah.
I also want to know about the first experiment, like the dry lab.
Okay, yeah.
And, when do you want that?
I think that was for next Tuesday.
Okay.
Because that's going to help you next Tuesday. It's basically a whole bunch of math, right?
Yeah, reaction yields, atom economy.
Yeah, that sort of stuff.
Yeah.
If you're having any problems, just let me know, and we can Set up
I
a-
haven't really like put pen to paper on it yet, so just wanted to know when it was supposed to be in.
Yeah. Okay, let me see here. No, you don't need to find out the names of the things in the dry lab. So what was the, I can't think of an example. Because if it's just a product, yeah, you just basically need the molecular weight, the properties, and all that sort of thing. So, like, let me think here. I have to dig that up. Let me. Dry lab. So the dry lab, I'm going to share this right now. New share dry lab. So for each one of these things, like if you make a table, you could just call, say, okay, it's already got the name for that. So, but this product here, you don't need to name that. That can just be the name of the, all you need to really figure out for this is what the molecular weight would be. Totaling up the atoms and just calculating that out. You don't need to know the name of, so enone, this one here is that. And again, you just need to figure out the molecular weight of it. You don't need to know the density. Because it's that won't be in any of the literature. So just find out the molecular weight, and from that you can calculate out the since you know the grams, you can calculate out the moles or the millimoles, and then once you've got that for all of the various components, then you can figure out the equivalents, which one's the limiting reagent, that type of thing. And this is just the product. You don't need to worry about the name for that either, just the molecular weight. This is, I did this reaction actually in grad school. So that's why I just used my exact old protocol from my lab manual for that.
So then for the table where we have to do like molar weight, millimoles, and then there's like the physical properties and the safety info, like do we just leave the safety info and the physical properties out of it?
Right. So exactly. So is there a table at the very, I think I did a table at the top. Right. So for, oops, what have I done? Yes. So this is a holdover from, so yeah, don't worry about this at all. And physical properties, don't worry about any of this. The only thing, if your starting material's got a density or if it's got a concentration for it, then you can put that there, because that's going to help convert between, say, a mass, in the case of density, between a mass and a liquid. And in the case of a concentration, if it's an acid, you can use the moles per liter to determine, because that's what molarity is. If you've got X liters, you can calculate out the moles from that. So those are, yeah, you don't need to worry about this, forget about that column at all. And it's only if there's a density or a concentration that you need to worry about for that.
What's the molar ratio there? Like,
Okay, so,
I
right.
need to like actually like look at it probably. That'll make sense, but
So your starting material, if you've got, here's the molecular weight. You've got 10 milliliters. So you're going to use the density to convert that into grams.
okay.
And then with the grams, divided by the
Moles.
molar weight, that's going to give you your number of millimoles, so 91.
Okay.
And then if you've got 91 millimoles of starting material, 300
Yeah,
millimoles of
I'm
this.
retarded.
No, no, it's just we usually typically don't talk about the equivalence or molar ratio. Sometimes this is just called the equivalence. It's the stoichiometry of the reaction. So this will be the limiting reagent, and this one's in excess by 3.9. So that's basically how you would, so that's part of the table that you'd want to have. Yeah.
And we don't put like solvents or anything in this table. It's just reactive products. Like
the solvent you do want to include, yes. So I should have made a better table. This is okay. So for example, here, so you've got your methane sulfonyl chloride. You've got your pyrrolidine, and you've got what, triethylamine, I think, and dichloromethane. So grams, milliliters, millimoles, equivalents. And so with the three actual reagents, there's going to be some sort of equivalency here. This could be 1, this could be 2, this could be 3, whatever it might be. But with your solvent itself, you're going to use, say, 20 milliliters of solvent. And it's based upon, you calculate this based upon dichloromethane's concentration is 0.2 molar with respect to the limiting reagent. So whatever the limiting reagent is, say it's this, you need to make a 0.2 molar solution. So the millimoles of this divided by the milliliters of this should equal 0.2. So for the solvent. So this would be 0.2 molar. So it's a way of, when you're doing a reaction, keeping the volume of solvent you would use constant from one reaction to another.
okay.
And this is one of the problems, actually, when it comes to process chemistry, when you scale stuff up on an industrial scale, you can't use the same sort of, you might have optimized your reaction at say, this 0.2 molar. And then it becomes a whole other problem trying to optimize it, because you don't want to use that much solvent in an industrial process. But anyway, yeah. But yeah, that's a good point. I'm sorry, I didn't think about you don't need the physical properties, and you don't need the, if they're corrosive or any of that, because none of those things that were there are commercially available. So that data isn't going to be there. Does that make sense? Okay, good. So I will see everybody on Tuesday if I don't see you before then.
I had one last question.
Okay.
The lab on Tuesday, is that an in-person lab?
Yes.
Okay. I have to drive, like, because we have class before that. Can I just leave class a bit early then? Because I live in Portage.
Oh, okay. So did I put you in the afternoon, the later slot or the earlier slot?
I'm in 1:40 to 4:40.
Oh no, I sent out a
Oh, okay.
let me see here. I'm going to share something, a new share here, because we're only allowed 2 people in the lab at any given time.
Right.
So, so next Tuesday, I'd placed Kirsten and Josh first between 1:30 and 3:45, and then you and Brock at 3:45. It's not even going to take 2 hours, I don't think.
Oh yeah, that'll work. Like driving there, that'll work.
Yeah.
Okay, thank you.
And so I think I did that for each. Yeah. So there's only 3 labs, and it'll be like a late start in each for you, a late start in each case.
Okay. Oh yeah, sorry. One more thing. What's due? Is it just the dry lab bonus assignment and the reducing reagent?
At different times, yeah, those are the first 3 things that we're doing, right?
Okay. Okay, that's all.
I
Thanks.
think the immediate thing is just the dry lab.
Okay.
So like, did the people that aren't coming into that lab on the 19th, do we have a responsibility to do something related to the lab at that time, or
No, it's basically
we're doing like half as many labs because of COVID, or
right.
I just tried to scroll on your screen.
Oh yeah, so I put like you'll be February 2nd.
Yeah.
And then March 2nd.
I just like, yeah, I didn't really look at it yet, but I wasn't sure if we were all like working on one big experiment in like sections or.
No, I've basically this time I've done it so that we're actually gonna get specific. I mean, do a reaction which is relative to the course, but learn a specific technique of how to do it. So the first reaction is basically working under a nitrogen atmosphere and using syringes. The next reaction is going to be using materials that catch fire in air. And
That's fun.
So we'll be doing all of the reactions under basically a nitrogen atmosphere and that sort of stuff. We're slowly building things up.
Okay. Yeah, I think we did a little bit of the nitrogen stuff with Yan.
Okay, good.
In inorganic 3, 4, I don't remember.
Okay.
No.
Yeah, so for the weeks where you're not in the lab, you basically got time to
brush up on organic 1 and 2.
I guess. Yeah. Alrighty.
Perfect. All right, I gotta skedaddle.
Okay, sorry for keeping everybody a bit later.
No worries.
Bye, Dr. Hill.
Have a good day.
Bye, Dr. Hill.
Bye-bye.